Hi there, I hope you're all doing fine and you enjoy your summer or winter, depending on where you are on the globe. There is a rather common data analysis scenario for which I realized that there are not so many well-prepared resources on YouTube. Namely, how to understand and measure the association of two categorical variables. More often than not, our datasets do include categorical variables that encode qualitative features of our data and take a limited number of possible values. For instance, the type of car based on the number of gears or the number of cylinders in the well-known mtcars dataset are two such categorical variables. There are numerous association measures invented and used in scientific fields such as linguistics, biology, and physics. The ones that you see in this shortlist are well known in these fields. But before presenting how to calculate these association measures with Julia, in this video I will spend some time on setting the stage. Namely, that we are going to see together how to create a contingency table in Julia with frequency counts for pairs of categorical variables in a dataset. Then, a series of relatively short videos will follow in which I will be explaining how to use and calculate the association measures in this list with Julia. But let's take first things first. What is an association measure and what is it used for? An association measure is a single index or number or score, if you like, that is used for measuring how strongly two categorical variables are associated. Namely, how the frequency counts of all levels in one of the two categorical variables are related to frequency counts of the levels in the other categorical variable. Recall that the level of a categorical variable is one of the possible values that you can assign to a data point regarding that categorical variable. For instance, red is the level of the categorical variable existing colors. Another level is green, and so on and so forth. To be able to say that two categorical variables are related or associated to each other, you need to be able to measure and report how the values of two or more categorical variables co-vary, which means how the frequency counts of each level of the categorical variables varies in the same or in a different direction with the levels of any of the other categorical variables in a dataset. I can see many of you wondering right now, it kind of sounds similar to the correlation coefficient, right? And yes, you are correct. It indeed resembles the terminology used for creating a linear regression model, but the terminology changes slightly. Now, instead of correlation, you need to use the term association, and instead of correlation coefficient, you come across the term association measure. Now, moving to a Pluto notebook I prepared for this video and that you will be able to download from my GitHub account. Check out the video description below, you'll find the link there. There are some common steps in calculating any association measure for two categorical variables. The first step to calculate an association measure is to understand how association measures are actually calculated, which means that you would need to know what the contingency table is. Of course, Julia includes packages that provide functions for calculating directly most of the association measures that you just saw, and you won't need to know how to create a contingency table. But in order for you to be an informed user of these association measures and to be able to choose the right one for your case study, it is essential to get acquainted with the notion of a contingency table. A contingency table is a two-dimensional table whereby each of the rows represents one level of the first categorical variable and each of the columns represents one level of the second categorical variable. We will have a look at contingency tables in a minute. Let's load the well-known mtcars dataset from the R dataset package to work with its categorical variables. As you can see, I already imported a number of packages that you will be using for running this notebook. R datasets import most of the standard preloaded datasets that are available when loading R. And the mtcars dataset is a freely available dataset in R that is used as a starting point for many tutorials. As you can see, it includes 11 design and performance features related to each of 32 car models from the year 1974. For instance, the miles per gallon consumed by these cars, or the number of cylinders, and so on and so forth. To get a good overview of these variables in the dataset, you can use the describe function in Julia. The output is a table with the most common descriptive statistics for all columns of the dataset. The most important columns of this output table for us is the column L type that displays the data type of the column. As you can see, not all Julia types encode accurately the real statistically meant data type of the variables. For instance, the number of cylinders is not really a numerical variable but a categorical one. The possible values are 4, 6, and 8, as you can see here. It is simply read in Julia as a variable with values of type int64, namely integers. The same applies to the last 4 variables on the right. VS, the transmission type, the number of forward gears, and the number of carburetors. All these variables should be encoded as categorical ones, since in each entry their value are one of a discrete number of categories. What this means is that, for example, between the values 0 and 1 of the type of transmission, there is no real numerical difference or distance between them. To be able to work with such type of data, you need to first assign to these columns the right statistically meant type as it is expressed in Julia. It is the corresponding factor type in R, if you know, that we are looking for. So in Julia, as far as I've seen, a common way to represent categorical data is through the categorical array data type. This data type is also recommended in the documentation of the dataframes.jl package as a type to express categorical variables. For creating the contingency table, I will focus on 2 of these 4 variables I just mentioned that are of categorical nature. I will focus on the number of gears and the number of cylinders. To convert the data type of the 2 columns to categorical array with a one-liner, you can use the pipe macro, the combine function that is similar to summarize function in R. Choose the 2 variables and forward them to an anonymous function that converts the numerical values to strings and then to categorical array. The argument rename calls is set to false to avoid automatic generation of column names and to keep the initial column names. Julia is surprisingly mature in data wrangling, and I dare to say that it almost matches the level of maturity of the dplyr dialect in R. As you can see now, we have a categorical array. Now it's about time to create the contingency table. To do that, let's use the FreqTables package and its FreqTable function that takes the data frame as its first argument and the 2 variables as the second and the third argument. And since the output of the cell is not displayed well on Pluto notebook and some of its contents is hidden, I use here the with_terminal function loaded from the Pluto UI package, followed by a do block of code to be able to display the whole content of the table as if it were in the terminal, as you can see now. Let's have a closer look at the table. The cell at the first row and the first column has a value of 1, which means that there is only one car model that has 3 gears and 4 cylinders. So the numbers here represent frequencies of the car models with the combination of gears and cylinders in the corresponding rows and columns. Now, if you want to see the joint distribution of the cells in the whole table, you can use the prop function on the created contingency table. As you can see, the most frequent combination of gears and cylinders in cars underscore table is the cell in the third row and first column, whereby car models with 3 gears and 8 cylinders constitute 37.5% of the whole distribution. Usually, a contingency table includes an additional row and an additional column that contains the marginal frequencies of the rows and the columns respectively. Also, the contingency tables that we all have in mind include the cell with the total sum, it is 32, that we expect for all the car models in our case, which is in the leftmost corner at the bottom, completing the table as you can see. Now, let's add these 3 additional elements to the existing table. First of all, you need to take the sum of each row and the sum of each column. You can do that with the each row and each col functions embedded within the sum function. So, what the line for defining the col sum says is, take the values of each row in a column and then sum them, and do that for all the rows of all columns. Respectively, take each cell of a row and sum their values, and then do that for all rows. Now, we either add the row sums first to the right of the existing frequency table cars underscore table, and then add the last row of the final contingency table, or we add the col sums first to cars underscore table and then add the last column to the right. Let's take the first option here, namely to add the last column to the right first before adding the last row. You can use the hcat function with 2 arguments. The first is cars underscore table and the second is row sums. The next step is to create the last row of the contingency table. To do that, you need to first create the cell with the total sum. And to do that in Julia, there is, in my opinion, some unnecessary complication. Since in the end of the day you need to concatenate a single number and the named array, that is the col sums, you also need to create a named array for the total sum cell with a compatible type. To create the named array, you need to create an array that has as its name a string of type categorical value. That is why I have to include the tuple with the name of the newly created array that has only one member, number 32. Now, there is a high probability that this is done in a simpler way. I could probably convert the whole cars underscore table from a categorical array to a simple array of integers, and that could make things easier. If there is another way that would allow me to keep the categorical value types for the contents of the contingency table, I would be happy to learn about it. So go ahead and correct me or suggest a better way of adding the margins. Okay, but we're not done yet, although we are almost there. Now you simply concatenate the 2 named arrays, col sums and total, and you get the last row. Next stop is to vertically concatenate the cars underscore table n array with the last underscore row to get the final version of the cars table. If you noticed, when adding the last row, the row names have changed, while the column names had already been changed in an earlier step, and that needs to be corrected. So the last move is to change the names of the columns and rows of the table so that it is presentable to other people in the community. To access the row names of a named array, you use function names that returns a vector of names for the rows and columns correspondingly. To get the names of the rows, you select the first member. As you can see, it's 4, 6, and 8. Here the type. To get the names of the columns, you just have just take the second member of this vector. Unfortunately, there is no row names as in R, but I don't feel there is a real waste of time here. Now, to be able to add the last row name with the row sum, you need to convert the int64 array with the row names into strings so that the row names array becomes a string array. You will do the same for the call names. And the final step is to make the cars underscore table underscore final underscore array a little bit prettier, and for that reason I use a lower level constructor to be able to assign the row names and call names plus the dimension names. And now you have the final version of a contingency table, as we all know, also in R or in other languages. That's it for now. I hope you gained something out of this video, particularly with respect to categorical data and how we encode them in Julia, and how to handle them also with various functions. So I'll see you later.